Okay, off we go. Let's see, am I recording? Yes, okay, good. So, here's picking up where we left off. We were talking about lines and planes and such. So here's another example. Let me go in full screen mode. There we go. So another example. We've got a line here, and what we know about the line is we know it goes through a certain point. And then we also, okay, well, I'll go ahead and circle. So we know that it goes through that point, and we know that it is parallel to these planes of which we're given equations, right? So we want to find the equation of the line that fits this description. Okay. All right. So in order to do that, now, of course, to understand a line, we need to have a point that the line goes through, and we need to have a vector parallel to the line. Well, we already have the point. That was given, right? So we really only need to find this vector. And in order to find this vector, we got to think geometrically. What do we know about that vector? Specifically, what do we know in relation to things that we can get our hands on, right? So let's start by looking at the givens a little bit more carefully. So, for example, this first plane. There's the equation of our first plane, and I want to remind y'all, when you see the equation of a plane, you immediately know what the normal vector for that plane is. You go back up to here, right? When you have the equation of the plane, these coefficients are your normal vector, right? So, so that means I know, for example, I can see these coefficients right there. There's a 1, and there's a 1, and then there's a 0 that I didn't bother writing down, of course, because it's 0. And that tells me that this first normal vector is that 1, 1, 0. Okay. All right, likewise for the other one. So effectively then, we are given this pair of normal vectors. We are given these two vectors. We are in search of, for the moment, that vector there. Right? And so now begins the puzzle. Right? So we're given some geometric things. We've identified that we need a geometric thing. How geometrically can I relate those? Right? Okay, so the case I'm going to make here as well, I know that, for example, this vector is perpendicular to that plane. That plane is parallel to that line, and therefore the vector. And there's a sort of a connect the dots argument that you can think through. If the blue vector is perpendicular to that plane, and if that plane is parallel to the green vector, geometric appeal, right? Just think through how does the geometry work? That means that N1 and V have to be perpendicular to each other. Everybody buying that geometric appeal? You got to see it from the picture, right? And then likewise, N2 is perpendicular to that second plane. That second plane is parallel to V. Again, connect the dots, and therefore these must be perpendicular. So, saying it a little bit differently, what we know about V is that it's perpendicular to two known vectors. I need to find now then a vector perpendicular to two known vectors. We have a tool that does exactly that, and that's the cross product. So, the big idea, again, I'm going to find my V vector. I'm going to choose, you might say, my V vector by taking the N1 and the N2 and using my cross product tool. And game over, right? So now we've got the A point on the line, we've got the V direction vector for the line, and you assemble the parameterization. All right. Okay, so let's look at these last two examples that we just talked about. Both of these examples, this is, of course, at the end of last lecture. Both of these most recent two examples have what I'm going to call a transitivity, sort of, for lack of a better word, sort of a transitivity argument involved. So, for example, in this argument, I argued that the plane is perpendicular to the normal vector, and the normal vector was perpendicular to the y-axis, and therefore I could draw a conclusion about the plane and the y-axis. So you see what I mean by kind of a transitivity of sorts. Right? And then likewise, down here I argued a transitivity of sorts. The vector is perpendicular to the plane is perpendicular to this other vector, and therefore I drew a conclusion about the relationship between these vectors. So here's the thing. Transitivity, air quotes, transitivity arguments, a little bit dangerous. They're not all as obvious as you might sort of casually at a glance think they are, right? So here's a couple of fun little counterexamples. Everybody okay? Okay, yeah, all right. Okay, so let's see here. So this vector is parallel to that plane, right? And let's see here. This plane, whoops, I wanted to hit the color here. This plane is also parallel to that vector. If you were to just kind of buy into, careless, transitivity argument, you might think that would mean that V and W have to be parallel. And that's obviously not true. Look at the picture, clearly false. Obvious nonsense. Right? So just because you kind of connect some dots doesn't mean that there's actually a conclusion there to be had. So beware of that kind of thing. Likewise down here, let's see here. So P and Q are perpendicular planes. Q and R are perpendicular planes. Does that mean, rhetorically I ask, does that mean that P and R are perpendicular? No, obvious nonsense. At a glance, easy to reject. It doesn't mean they're parallel. It doesn't mean they're perpendicular. It just doesn't mean anything. Yeah.
In the previous example, I'm confused how, the vectors.
Talking about this one here?
No. The previous one.
Okay, the previous, yeah. This one here?
So, N2 is like this plane, and this is normal, this is the line, it's perpendicular.
Yeah.
But I'm confused on how, this is also perpendicular to the vector.
On how, what now?
How can two different planes have normal vectors that are perpendicular to the same line? The same vector?
Well, there's three different directions, right? And so here I'm going to point at you, right? Now my left hand is pointing perpendicular to the line that I'm pointing at you with, and that vector is too. And so both of these vectors are perpendicular. Yeah. Does that make sense? Yeah. So very critically, it's because we're working in three dimensions. Yeah. Absolutely. Good question. Anybody else? Okay, so heads up about these little landmine, tempting, again, if you just write it down on the page and don't think about the geometry, on the page, just, from the notation, it almost kind of feels like they ought to be true. You got to think it through geometrically. So, by the way, I suppose it's possible that I could try to enumerate all of the possible transitivities of parallel and perpendicular and lines and planes, and what if it's a line to a plane and a plane to a line, or a line to a line and a line to a plane? Oh my gosh, there's too many possibilities. We can't enumerate all of them. Right? And if I could, you couldn't remember all of them. Right? So my simple rule for addressing this is think it through, and if you want to cite a transitivity argument, go ahead, as long as it's valid, right? If you claim it's true and it is true, fine. When it comes to these transitivity arguments, right? But you do, of course, have to actually be right about it. Okay, so be careful. Heads up. Okay, here's another argument. Now, y'all might recognize this as being closely related to a homework exercise. So this is just kind of capitalizing on the result of that exercise. If you want to parameterize a plane, and keep in mind a parameterization, the way I like to think about that is it's a point generator. I've got to be able to write down a formula that describes the locations of all the points in that plane. Okay, so how to do it? Well, I'm going to need more than what I needed to parameterize a line, I'm going to need a point on the plane, and I'm going to need a couple of different vectors parallel to the plane. And by way of this couple of different vectors, notice that I can describe any other point on the plane by really simple construction. If I start at the given point A, and if I go some multiple of one of my direction vectors plus some probably other multiple of the other direction vector, keep in mind, those are just multiples of our given direction vectors V and W. Right? Well, dark blue plus light blue gets me to that point R. And this can be done for any point in that plane. Right? If it's farther away, then S and T are bigger. Right? Or if it's, what if R is what maybe over there on the left? Well, S and T might be negative. Or maybe S is negative and T is positive, right? Various different possibilities. But no matter where you are in that plane, there will be values of S and T that get you there by this construction. Let me pause for a second. How are we doing? Does everybody see the geometry of this? Everybody's happy? Yeah, question.
I thought that parameterization means that you have to have like multiple equations, like x equals this, y equals this, z equals this.
Well, so that's a coordinate form of a parameterization. Really, a parameterization is position as a function of parameters, right? And yes, you can describe position with coordinates, but you can also describe position as the position vector, and of course the position vector has coordinates, right? So coordinates are a useful tool in some situations, but very often, such as in a case like this, they're just kind of fussiness that we're having to deal with when in fact vectors and vector notation get right to what is actually most relevant. Does that make sense?
Yeah.
This is a more efficient, basically, way of thinking about it. Yeah.
Do V and W have to be like perpendicular? Or
That's a great question. They don't have to be perpendicular. They can't be parallel. Right? I guess more to the point, they can't be dependent. Right? So they can't be parallel, none can be zero, etc. But as long as they're independent, totally fine. All right. Okie dokie. So, now one interesting thing about this, you'll notice, is we needed two parameters to make this work. Right? I couldn't do this with just a single parameter. And fundamentally, the reason why is because my plane is two-dimensional. So this is different from a parametric line. A parametric line or a parametric curve, one parameter, because curves are one-dimensional things. Two parameters for a two-dimensional thing. I hope that makes sense. Is everybody happy with that? Okay. All right. Okay, so quick example. Be real quick about this. We've already entertained this question of if you have 3 points and being interested in the plane that contains those 3 points. Previously, when we saw an example like this, our goal was to find the equation. And to find the equation, we needed a normal vector, so we had to take a cross product at some point. Here, we're not, because here we're interested in a parameterization. Parameterizations don't require a normal vector. All they require is a couple of direction vectors parallel to the plane in question. So this is actually a pretty straightforward, I would say this is even easier question than we saw before. You pairwise subtract. Now you've got a couple of direction vectors. Pick any one of these. Doesn't matter. I'm going to use A just because it really doesn't matter. But any point in the plane. Now you got a point in the plane, a couple of direction vectors, and per above, there is my parameterization. Okay. All right. Okay. There's various questions that can be asked about how to find a distance from one thing to another thing. Point to a line, point to a plane, a line to a line, etc. Right? There are tools to be used in answering questions like this, and the way you use those tools, to a certain extent, is sort of a little puzzle of figuring out how can I take the tools that I have and use them to get the thing that I'm interested in. So I'm not going to go through all of these, and as you see, I have these designated as for students to read. So there are a lot of little details that I think y'all can totally read yourselves. Time being a factor and all that, as usual. So I just want to point out a couple of specific highlights. So in this first example, we are given a point. We're also given a line, by which I mean maybe we're given a point on the line and a direction vector to the line. So that's what we're given. And our goal is to compute the distance. How far is it from the first point to the line defined by the second point in the direction vector? And thus begins the puzzle. So details, of course, and again, that's for y'all to read. The big picture strategy on this one is to first look at that vector, which you get by pairwise subtracting. Then find the projection vector, subtract the projection from the original, and of course that subtraction results in that, whose magnitude is clearly the distance that I want. Right? So that's just kind of the strategy. That's the puzzle aspect. That's how you solve the puzzle. Make sure to think through. Okay, do I know how to compute that projection, and how would I do that subtraction, and how do you compute magnitude, et cetera, et cetera. But strategically, that's the idea. Now here's a different approach to that. This is very clever. This is super clever. Sometimes when you're interested in something, compute something else. So in this question, I've been asked to compute the distance, and so I tell you what, I think I'm going to go ahead and just compute this area. It's not what we were asked. But I'm going to compute it in two different ways. And first argument I'm going to make is this is an old high school geometry argument. If you want to know the area of a parallelogram, it's the height times the area of the base, right? I'm an old news formula from high school geometry. Make sure you're comfortable with that. So we write that down. And then here's another way that I can compute that area. After all, I've got a couple of vectors defining a parallelogram, and we have a formula from the previous section that says the area of the parallelogram is the magnitude of the cross product. Right? So now I've done two different computations of the thing that I'm not interested in. So again, this seems like we're going way down a road of irrelevant. Right? The reason this is not irrelevant, what makes this super clever, is that if I compute something two different ways, those results have to be equal to each other. And knowing that those results are equal to each other allows you then to solve with a little bit of easy algebra in this case for the thing that you're interested in. So this is a tried and true, clever move, sort of mathematical strategy of how to compute things sometimes. Compute something else and then connect the dots. So specifically, the idea is to figure out what some other thing is for which the thing you're actually interested in is relevant. Right? So I picked area here because I knew distance that I'm actually interested in was going to be involved in at least one of those calculations of what I was actually looking at there. So anyway, figure out how to involve what you're interested in a different question and then take it from there. Okay, so I think it's a nice little strategy. So real clever idea here, if you have a couple of parallel planes, well, parallel means they have the same normal vector. And if you know a point on each of the planes, really what you're interested in is looking at that blue vector and finding its component in that normal direction. So again, this is how you solve that particular puzzle. Yeah.
On the last part,
Uh-huh.
are you saying that the length of B is equal to the area?
Say again?
What was like the first? You're saying like the first term is the length of B or the magnitude of B, right?
I'm sorry, you got to speak up just a little
Like
bit.
the magnitude of B, you're saying that's equal to the area?
No. I'm saying this product is equal to the area. Yeah. And that's just, the magnitude of V is that distance, and D is, colors. D is that distance, and I'm saying green times blue gives me that gray area. Yeah. Old high school geometry formula. Is that cool? Yeah. All right. Okay, so again, different little clever use of pre-existing tools to answer a question. It's a different sort of little puzzle move. This last one is really very clever. This is very clever. This is not the kind of thing that I think most students would have thought of on their own. And so, again, this falls into the category of don't hold yourself to the standard of, I should have been able to think of this one myself. No, on this one, hold yourself to the standard of, can I follow and understand and add to my own personal toolbox this very clever idea that someone else thankfully thought of for us. And so here's the clever idea. If you have a couple of lines, skew lines, that is, not parallel, non-intersecting, just kind of the most unrelated, right, uninteresting pair of lines. It's kind of random lines. When you have that, if you think about it, these two vectors, you can take their cross product. Their cross product will point in a direction that's perpendicular to both. And if you use that as a normal vector, then I claim that you can make parallel planes. Right? Parallel planes that contain these two lines. And you just gotta, think through the geometry here. Well, let's see here. How do I know that there is a plane that contains L1 like that? Well, if there's going to be such a plane, I need V1 to be perpendicular to N. Right? That's the geometric sort of need. As long as V1 is perpendicular to N, then I can find that plane that contains it. And well, of course it is, because it's a cross product. Again, super clever. Right? I didn't think of this on my own. Somebody showed me this when I was y'all's age. Yes?
How do you know they're parallel and not the same plane?
How do what now?
How do you know the planes are parallel and not just the same?
Oh, well, if they were the same plane, then these two lines would intersect, which means they wouldn't be skew. And so the assumption is that they're skew. Now, that said, if they were intersecting lines, this would reveal that they're contained in the same plane. And yes, that would conclude that the distance is 0. So in some sense, we don't even really have to worry about that. But yeah, it is technically eliminated by the assumption. Yeah. Yes?
Are we expected to find the equation of these planes or not?
Well, all you're going to need is to be able to do this calculation right here. Because once you realize that you're looking for a distance between parallel planes, then that's all you really need, is that right there. Yeah. Okay. Yes?
So in this case, like for this last example, would this just be the length of the normal method?
Nope. The distance is this formula right here. So the normal vector is involved, right? But the normal vector doesn't tell the whole story. That's right. Yeah. Okay. Okay, so fun and games, puzzles with the various tools that we've seen here. These are great little mathematical weightlifting kind of exercises where the more you use these tools, the more you'll get proficient with using these tools. So y'all will have some homework exercises that are kind of along these lines. No pun intended. Okay, moving along. So let's see here. We're into 1.7 now, new coordinate systems. First of all, I want to take a quick moment to appreciate some wonderfully nice and convenient properties of rectangular coordinates. And so first of all, rectangular coordinates are unique. Not only is it true that if you give me coordinates, that determines a point, but furthermore, for any point, there is exactly one pair of coordinates in rectangular coordinates that describes that point. So these rectangular coordinates are unique. Seems like a silly thing to say, right? We're so accustomed to rectangular coordinates, and of course they're unique, and like what a waste of breath. Here's another seemingly obvious statement. There's a really nice relationship between rectangular coordinates and coefficients in linear combinations of the standard basis vectors, and that's a really nice construction. We use that in various ways. And then here's another, very closely related, of course, a really nice feature of rectangular coordinates. If you know rectangular coordinates for a couple of vectors, and you want to take a linear combination of those vectors, you can just take the same linear combination. Let's see here. You can take the same linear combinations of the rectangular coordinates to get the rectangular coordinates of that linear combination. Right? It's really convenient. Very handy. And again, something we're very accustomed to. So why belabor the obvious? Well, it's because these are properties that we're going to have to say goodbye to in studying other coordinate systems. Right? None of this works. None of what's on the screen works in these other coordinate systems we're about to talk about. So heads up, don't play too fast and loose with these non-rectangular coordinate systems. These properties fail. Okay, starting with polar coordinates. Polar coordinates, I think a lot of y'all have probably seen polar coordinates in some sense, to some degree, here or there. There are different ways to think about it. There are different ways to mess it up just a little bit in ways that are actually problems. So here's the way I like to think about it. I like to think of polar coordinates in relation to a function. Specifically, I like to think of polar coordinates, we're going to call them r and theta. Right? Polar coordinates are the inputs into a function that produces, a given point in the xy plane. Okay. Now, what role do these play in the function? Well, they play the role. I think y'all mostly seen this before. Theta represents angle measured counterclockwise off the positive part of the x-axis. R tells you how far to go in that direction, with the understanding that how far is not a distance. And that's why I put the air quotes around how far. This is a really subtle, awkward, but really important aspect of polar coordinates. R is not a distance. Sometimes it is, right? But R is a coordinate. R can be negative. If R is negative, that just says go the other direction, right? If R is negative, just go that way. Perfectly fine for R to be negative. Okay. How are we doing? Is everybody with me so far? Okay. So what's nice about this is a sometimes really convenient way to describe a location, right? If I were here and I wanted to describe where I am, you could do x and y coordinates, I suppose, but look, if I want to go from the origin to that point, the easiest way to do it is tell me, look, which direction should I go, and then how far do I go in that direction? It's just very handy. It's very natural. Okay. All right. Okay. Here's the function that does it. Now this is a nice little exercise. Think about how to use this picture to derive those equations. And that's just a little trig. You do want to make sure that you're good with that trig. You do want to make sure that you can put it together and come up with this conclusion. As always, ask me in office hours if you have any trouble with this. But make sure that you're good with not only that this is true, but why this is true. Okay. All right. Now there's a bunch of little things that have to get said that, again, keeping in mind how much we have to do in this course, and, chapters 6 and 7 are stout, right? And we need to preserve as much class time as we can for chapters 6 and 7. So I think this is a pretty easy read. I'm going to let y'all read this part on your own. I'm just going to very quickly point out that when you have an angle, alpha, thus indicating a direction, right? Then you could just go 5 in that direction, and boom, that gets you to this point. And then I make the innocent observation that if I were to add pi to that angle, just go around another half turn and say, well, what happens if I go in that direction? Well, if I go in that direction, I'm just going the wrong direction, right? I'm going, but not just the wrong direction, I'm going exactly the wrong direction. And because you're going exactly the wrong direction, going backwards gets you to the point, same point. Right? So this is an example of the non-uniqueness, and then you can also add another pi, and that gets you going back in the right direction, et cetera, et cetera. So details to be thought through, but heads up for this little phenomenon. That is a significant point. Again with the accidental puns. Sorry about that. And this is also a pretty straight read. I'm going to let y'all look at. Whoops, I missed it. This right here, pretty straight read. Make sure to read this. Just do keep in mind that if you write down a pair of coordinates, it is not necessarily clear which coordinate system you're talking about. Right? It is tempting to look at 2 comma pi over 6 and think, well, pi over 6 is clearly an angle. And I mean, that's probably a good guess. But don't forget, pi over 6 is a real number. That's a perfectly fine, perfectly acceptable real number, and that could be y. That 2 comma pi over 6 could be x comma y. And if you don't indicate specifically otherwise, what you're writing down is vague. Right? So in any situation where there's more than one coordinate system in play in the context, it's a really good idea to just specify, and look how easy to specify. Okay, this one is really tricky. I find in this example I'm fighting against a lot of bad ideas that have been pushed into student minds by high school math classes. A lot of wrong ideas. So in particular, very often I see this equation here misrepresented as r equals square root of x squared plus y squared. And that's not true. Sometimes it's true, right? It might be true. But as a broad statement, as a matter of universal fact, no, it's wrong. And the reason why is you got to keep in mind that symbol, the square root symbol, does not mean whichever square root you feel like. It doesn't mean whichever square root might be most appropriate in context. That symbol means the positive square root. That means positive, right? If you want to talk about both of them, you could say plus or minus, but now it's still vague. It's still that you haven't indicated which one you're talking about, right? So if you just say r equals square root, it's just not true. That implies r is positive, and r need not be positive. So likewise, it's tempting sometimes. A lot of people like to solve for theta and write that it's arctan of y over x. That too is not true. There's a lot of different values of theta. Right? Arctan has a single value. Another common misunderstanding, a lot of people misunderstand that arctan means that it's a bunch of different values. No. Arctan means a very specific value. Arctan is always between negative pi over 2 and pi over 2. So again, it's just not true, right? Now, it's worse than this. It's not just that ambiguity problem. There's also the matter of how you put it together. So let's think about this point right here. That point whose rectangular coordinates, -1 and -1. Fine, nothing weird. I can compute r squared. I can compute tan theta, right, off of those formulas, no problem. Okay, so well, this first formula seems to tell me that r has got to be one of those values, and this second formula tells me that theta has got to be one of these many values. And notice the little algebraic move that I've done there. That plus 2 pi in is a way of indicating that you can add as many 2 pi's as you want, and those are all usable possibilities, right? I mean, those can be polar angles theta. So nice little construction. So the mistake that a lot of students make is to say, oh, well, I don't like these weirdo values, right? I like the easy ones, and so I'm just going to pick these right here. And I'm going to, because I'm allowed to choose, apparently, right? Can't I just choose the ones I like the most? And sadly, no. Because if you pick pi over 4, and in that direction you go a distance positive square root of 2. Whoops, I hit the wrong button there. If you go positive square root of 2, you're in the wrong point. Everybody see what happened there? So if you just take, formulas written down from high school math textbooks, you're going to get some wrong answers sometimes, right? And that's why the reasoning is invalid, right? That's why we call it, incorrect reasoning. It's because it sometimes, at least, gives incorrect answers. And I'll remind you, I've said it a bunch before. You're going to hear me say it a bunch again. We're much more interested in your reasoning than your answer, right? But I hope that makes sense. And again, feel free to come talk to me anytime you like about why is that? Why do we care more about reasoning than conclusions? And I'll be happy to go on at length. But that's what the course is about. So make sure not to commit little math crimes like this and like that. Oh, not that. The solving for r, r being a square root. That's a little math crime. Don't go that direction. Okay, what's on this page is mostly, I think this is not a good investment of time. Y'all can totally read those. This next one is a little bit more thoughtful. You got to kind of think through. And the big trick on this one is that for certain angles, right? So here's a range of values between 0 and pi over 2 for theta, right? Keep in mind that theta is not what you're taking sine of. We're taking sine of 2 theta, right? So this is when you're thinking through the details of this one. That's the sticky wicket. You got to keep in mind that even though theta goes from 0 to pi over 2, and geometrically that puts you in the first quadrant, 2 theta goes from 0 to pi. And as 2 theta goes from 0 to pi, sine of 2 theta does like this. It goes up to 1 and then back down to 0. Right? And so interpreting accordingly, now this is a test of my drawing ability. There you go. that traces out that first kind of petal, if you will, of the, y'all can probably see it coming. This is eventually going to be a 4-leaf clover kind of looking thing. And so that first leaf of the 4-leaf clover is results from looking at just those values of theta. Okay, so again, details to think through. You want to think through the rest of the remaining 4 quadrants. It's a good exercise. Do keep in mind sometimes R is negative, right? You can see that right here. R is sine. Sine is negative sometimes, right? So you got to think about how that factors in for the second range, and etc. Okay. All right. A little bit of fun and games with converting equations. This is mostly just algebra. I think this is very doable, very readable, so I'm going to let y'all read this. And again, as always, come to my office hours if you have any questions about any of that stuff. Okay, cylindrical coordinates. It's pretty much polar coordinates. And you can look at the picture down here. If you confine your attention momentarily to just the XY plane, notice it's pretty much just R and theta, right? So cylindrical coordinates start off with just R and theta. And the only difference between cylindrical and polar is that in cylindrical we're in 3 dimensions, and we have to recognize that you got to go up by some amount. That up is the Z coordinate. And so you just kind of attach that on at the end, right? And effectively you can kind of turn the polar coordinate system into a new 3-dimensional cylindrical coordinate system. Everybody see the idea there? Now, because we're piggybacking pretty shamelessly off of polar coordinates, I mean, free formula there, right? Free formulas here. That all comes along for the ride. All right. Okay, a few examples here. These first 2 are pretty, again, this is, make sure to read through the details here. These first 2 are pretty straight reads. Make sure that you follow those details. Notice, by the way, in this second one, I'm really just taking advantage of this formula right here, that x squared plus y squared is r squared. Right, so sometimes that's all you have to do is just use these conversion formulas. Okay. All right, I do want to talk about this next one a little bit. This is a little tricky, and there's different ways to answer this question, of course. How to get our hands on what this looks like. There is a really valuable observation to make about this equation. That's our foot in the door that's going to make this all work. You can see this is an equation in cylindrical coordinates. All the variables present are cylindrical variables. And one of the cylindrical coordinates is missing. There's no thetas in that equation. Turns out that's actually really, really valuable. So here's how. So let's think about what a value of theta means. So a fixed value of theta, I claim is, I'm going to think of it as being a half plane hinged on the z-axis. So, for example, something like this. So that is a certain value of theta. Let's see here. It's like there's like a door. The hinges are literally on the z-axis, and that door has swung over that way a little bit. So half plane hinged on the z-axis. Okay, so here's the thing. That value of theta, whatever the theta is for this half plane, how does that show up in the equation? Well, not at all. Not even a little bit. There's no theta in that equation. And what that tells me is that what the cross-section looks like, the surface that we're interested in, what does that look like in that half plane? It looks the same as every other slice in every other theta half plane. Theta doesn't show up in the equation. All the values of theta will give the same resulting cross-sections. Right? So So, in fact, that's pretty easy to draw a picture of. Now, again, here's a half plane, what I'm calling a half plane. And if you think about what this equation looks like in that half plane, z is a multiple of r. That's pretty easy. That's just a line. Right? But then we do have to remind ourselves, I said half plane because, we tend to think of r as being positive most of the time. It's just kind of an intuitively convenient sort of thing. But in fact, r does not have to be positive. R can be negative. And if r is negative, notice that means that z will be negative, which means we just get this part of this line over here. And so once you understand that all the cross sections look like that, you can kind of geometrically turn it around backwards and say, okay, well then I can take my cross sections. My cross sections are just lines like this, and I don't know if I can. Let me do this with my fingers. Imagine the line segment connected by my hands here. Just rotate that around the z-axis, and that makes your surface. All right, if you know what the cross sections look like, you can just rotate the cross sections to make the surface, and you get this cone. Yes?
Be a little confused on the drawing. Is the door's end supposed to be at like the ends of the actual circle?
No, it's just there's a problem in trying to draw infinite things. Right? I can't really draw infinite things because there is no edge, right? And so what we do is we tend to draw a finite part of that infinite thing, and then you kind of have to use your imagination. So so when I draw this half plane, what I mean is it goes infinitely in that direction, infinitely in that direction, and infinitely in that direction. Yeah. Is that yes?
Can you explain the drawing on the right again?
Well, I don't understand.
Like, can you explain the diagonal lines?
Oh, well, yeah, that's just this is the equation of a line through the origin. If you think of this as an equation in the ZR plane, and see, we are in the ZR plane, right? Then it's just, Z is a multiple of R, so straight line, yeah. Is that cool?
Yeah.
Okay, yeah. Okay, so it's a tricky one, but there's a nice sort of moral of the story, and the big moral, the big takeaway is if there's no thetas in your equation, that means that your surface is a rotation around the z-axis. And this is another one of these results that I think is totally awesome because it is glance simple. So notice that there's no thetas in that equation. Right? We didn't have to do any legwork. I didn't have to compute anything. Eyeball, hey, check it out, no thetas. And we instantly get a powerful conclusion that this surface is rotationally symmetric around the z-axis, and that's geometrically very, very useful as I've used it here. Okay, do be careful. This is a real quick comment. There's a temptation to use R as a radius. Like if someone says, "Oh, we're interested in a circle of radius R," that's a problem because R is a coordinate. Right? So, for example, imagine you're doing a question in rectangular coordinates in the xy plane, right? And someone says, "Okay, and the distance between this point and this point, we're going to call that distance x." Hey, no fair, right? X is a coordinate. We've already x and y are taken, right? Pick something else, right? You shouldn't call distances or areas or things like that by names that are already being used as variables. So likewise here, R, you got to keep in mind, will be used as a variable. So you got to think up something else to call the what you're going to want to call R, a radius of some circle or a sphere or something like that. So anyway, heads up, yes.
So is the equation for a sphere above it also doesn't have a theta? What line is that rotated around?
It's not a line. That in that case, it's still a rotation, but it's a rotation of a circle. And if you take a circle and rotate it around the z-axis, then you get the sphere. Yeah. Is that cool? Yeah. All right. Okay, spherical coordinates. Another coordinate system, a really useful coordinate system. This one's a little less of a freebie in terms of how to write it down. So let's be careful with this. First, we're going to talk about the angle that I'm going to call theta, that our book calls theta. It's exactly the same as the polar theta. Isn't that nice? And so that it basically tells you, in some sense, again, I like to think of this as a half plane hinged on the z-axis, loosely speaking. Now we're going to next think about this angle that I'm going to call phi. Notice, pronounced phi. You're going to want to call it phi, but more common is call it phi. Phi is this angle within that theta half plane. Right? It's measured off of the the positive part of the z-axis, and then measured toward the theta half plane. So I think it's important to observe then that you can't even talk about your phi angle until you've already decided what theta you're going to use. So theta, in some sense, kind of has to be chosen before you can even start the conversation about phi. Okay. And notice that between the two of those, right, those together define a direction, and then the third spherical variable rho says, again, air quotes, how far you're going to go in that direction, and that gets you to a point. Okay, and again, how far, it's awkward, right? Technically, rho could be negative. There's nothing wrong with rho being negative. And how far suggests a distance, which suggests it's positive, which it doesn't have to be. So it's an awkward little point of discussion. But anyway, there's that. Okay. Oh, and I'm sorry. I seem to be over time. Sorry about that. We are out of time. We will pick up here on Friday. Have a good rest of your day. See you later.